Here we're going to look at the so-called finite difference formulas. We're going to learn how to derive them. And again, the purpose is to produce, so we can produce an estimate of the numerical derivative of a function. So the setup is that we're given some data, and of course the data is coming from a function, but we only have certain values of the function, certain measurements. We only have the function evaluated at certain positions. In this case, we're using x, could have been time as well, right? So imagine there is a function that that is underlying all these points here, but we don't have access to that. Rather, we only have certain measurements so certain value of the functions evaluated as some xi's, right? And in the past video, we saw that we could use certain formulas like that approximate the derivative of this function with respect to x. So we call this f prime of xi, which again, it's abbreviation for df at xi dx, right? The derivative with respect to x, and that we approximated with some formulas. For example, one of the formulas was the forward difference formula of xi plus 1 minus f of xi. And of course, you divide here by our h, our increment h, where h was xi plus 1 minus xi, right? This was the so-called forward finite difference formula we covered in the past video. And the point of this video is to show how formulas like this one and other ones can come about. So we start from assumption that our function that generated these data points, which is again mathematically right as a function that maps the real axis to the real axis, so it's a function of takes input one coordinate and outputs a number. We assume that this function is smooth, meaning it has derivatives, right? Not all functions have it, but we'll assume that it has derivatives f prime, f2 prime, and so on. And what we're going to do here is to look at the Taylor series of the function f. And if you remember Taylor series from calculus, there are a couple of formulas actually. There's the forward Taylor series and the backward Taylor series. Let's write both of them. So the first formula is the forward Taylor series, which says that f evaluated at x plus h can be expanded as a series, and that's the name of it, is a Taylor series, which will be f of x plus h f prime of x plus h squared over 2 factorial, which is 2 f double prime of x. And let's write one more term, h to the third power over 3 factorial, which is 6 f triple prime, which again, triple prime is the third derivative of x. And you get the gist, right? And we have many terms. It's actually an infinite series. That's the so-called forward Taylor series. We also similarly, instead of taking plus h, we can take a negative h, right? The h doesn't only go one way. We can take a step backwards, and plugging in the same value for negative h. Now in this formula we have f of x minus h f prime of x. So minus h squared is plus, right? So we have plus h squared f double prime of x. Now h to the cube is minus again, so this becomes an alternating, right? So we have a minus first, and then a plus, and then a minus, and the next one would have been plus 2. So let's finish writing this one. H to the third over 6 f triple prime of x plus, again, an infinite number of terms, right? These two are the same formula. The only difference here is that we took the forward step. Here we're taking the backward step. So let's take the forward formula here as this example, and let's solve for f prime of x in our formula 1. What does this mean? We have f prime on the right-hand side here in the middle of all these things. We're going to try to manipulate this function, this equation, so that f prime appears on the left-hand side by itself, right? And if you go through this exercise, you can quickly see that f prime of x will be given by f of x plus h minus f of x. You divide this by h, right? Minus h divided by 2, f double prime of x, and plus other terms. So again, what did we do here? We subtracted f prime from both sides, so it's effectively this becomes f of x minus f prime of x, and we subtract this by its side, so this moves to the other side, right? And then once this is on its side by itself, we divide by h, which means you take this h, divide this fraction, right, these guys, so that's the term here. You also divide this term here by h, so this h squared divided by h becomes h, and so on. So this is a new series, right, where we isolated f prime of x. And here we see that, I rewrote the formula we used in our slides from the past video. This is a forward finite difference formula. Here you can identify the forward finite difference formula, right? So all you have to do is call the hi plus 1 to be axi plus h, right? So that will be, and if you plug this in, you will have the same definition of the formula above. So what we end up doing is we take this term in the series and we ignore this term. So that will be our forward finite difference formula. So let's write this forward finite difference formula more clearly. So that's f prime of x, and we can write, it's going to be approximated, right? So this similar term, mathematical term, as fx plus h minus f of x divided by h. So it's an approximation. But you can see that we are going to be missing this term, right? And again, we're assuming that this h here is a small step, right? Small, so let's say a 0.1, for example, 0.01 or 0.1. So this term is going to have h, so it's 0.01, 0.1. This term here actually will have h squared, so that's 0.1 squared is 0.01, right? This one will have 0.01, and so on. So the largest term in the series here will be 0.1, right? So the largest error, we'll keep the track of the largest error, so we write this plus a term, the largest term of which is order, so big O for order, h. That's the meaning of that formula, order h, is that the largest term, when h is a small step size, the largest term will be proportional to h, rather than being proportional to h squared, for example. Right, so this is how you derive the first finite difference formula, right? You take a small step in the x direction, you subtract f of x, and you divide by the step size. You're going to make an error, and the error is of the size, roughly speaking, of h. Now, notice that we started from this formula, formula number 1, the forward Taylor series formula. We could have started from this one instead if we wanted to, and if we did that, we would have ended up with the following formula, which is called the backward series, the backward finite difference formula, which is called f prime of x will be approximate or similar to f of x minus f x minus h divided by h. And again, the largest term of the remaining will be h. So if we only used this term to approximate, the size of the error will be, roughly speaking, order h. So this is the forward finite difference formula. This is the backward finite difference formula. The first level formulas, which both have errors of, roughly speaking, the size of h. Meaning, if I reduce the step size, right, my error will be reduced, roughly speaking, by the reduction. So in step. So let's look at the following equation now. Let's do this a different color. Let's look at this formula, f of x plus h minus f of x minus h. If we take this, starting from this Taylor series, right? So we're going to take this and subtract that. So this here minus this, right? And if we do all of that, you will end up with, and once you subtract them, we then isolate f prime again, right? So that's the strategy. So let's do the subtraction and then the isolation. So this will be equal to 2h f prime of x plus h to the cube over 3 f triple prime of x plus so on. Why is this, right? So because the plus terms cancel out, so if I subtract this from that, that means this subtracted from that is 0, right? This minus this is 2, this term. This is the same as that, so this subtracted from that is 0 again. So this term is removed, this term is removed, and you're keeping this term, and so on. And this is what ended up here. So once again, we're going to now take this and put it alone by itself on the other side, right? We're going to do the manipulations that allow it to do this, and we'll come up with the formula. F prime of x will be equal to f x plus h minus f x minus h over 2h minus, you have the other terms, h squared, right? Because once again we had to divide this h cube by this h term, so it becomes an h squared term, squared over 6 f triple prime of x plus so on, right? Or using the same notation that we had before, we say that f prime of x is approximately equal to f x plus h minus f x minus h over 2h. And of course, we're assuming that h is a small step size, so the largest term of this remaining series will be just the size of h squared. So we just abbreviate all of that, all those words in English by just writing in math, just order h squared. And this here is called the centered finite difference formula. Right? And you can see that the benefit is now that, assuming again h is a small step, say 0.1, now the order will be not the error, the largest term in the remaining series will be roughly proportional to order h squared. So if it's h is 0.1, this is going to be 0.01, as opposed to order h here, which was, if the h was 0.1, the error will be 0.1. So this has a smaller error. So generally speaking, centered finite difference formulas, which come from this kind of thing of subtracting the forward-looking Taylor series from the backward-looking Taylor series, have a better error behavior. They're more accurate. So to finish off the video, let's look at estimating the second derivative. And how we're going to do that is the same. We start from the Taylor series, which once again is up here, right? And in this case, we're going to add this to this. So we're going to get rid of these terms, right? We add a positive with a negative, which are the same thing, they become 0. And so we're going to end up with this term only. Of course, this will remain, but we'll subtract that aside, divide by h squared, and so on, and we'll estimate the value of f double prime, which is the second derivative. So if we do all of that, which I just said, we do this, so we add 1, oops, what happened here? And 2, right? We add the forward Taylor series to the backward Taylor series. We're going to end up with f x plus h plus f x minus h will be equal to 2f x plus right, the first derivative terms are negative with the positive, become 0, so we only have the second derivative term of x plus the third derivative one is also 0, right? Because once again, we are adding these two things, so this and that becomes 0. So all I have here really is a fourth order term left, right? So order h4. And once again, we do the same trick. We would like to now estimate, put this guy, isolate them, and put it on the left-hand side. And we're going to have to divide all the other terms on the right-hand side by h squared. So h to the fourth divided by h squared becomes h squared. So let's write this formula down. So f double prime of x will be equal to f of x plus h minus 2f of x plus f of x minus h divided by h squared plus an order h squared. This is also, this in effect, this is also a centered finite difference formula, but now we're estimating the second derivative, and so the error in this formula is also order h squared, which is pretty good. So again, this video gives you a gist of how to derive this finite difference formulas for center finite difference formula, backward finite difference formula, finite difference formula, first derivative, second derivative, and so on. All are based on this trick of expanding a function with Taylor series, and you have the forward and the backward way of doing that. You can add them together, and you try to isolate different terms by playing around with these functions.